Okay, cool. Okay. Yep. Okay, so today we have Caroline Juang talk to us. She's a fifth-year PhD candidate at Columbia University in the Department of Earth and Environmental Sciences, advised by Park Williams, who is currently at UCLA. And Caroline graduated in 2017 with a Bachelor of Arts in
Yeah, I'm sure. I'm working
Sciences.
on it.
And a minor in environmental sciences and public policy from Harvard University. And then in between college graduation and her PhD, she was a project coordinator at GSFC Greenbelt, where she launched and managed the NASA Citizen Science Project, landslide reporter, and she was mentored by Dalia Kirschenbaum. So yeah, she has been recognized as an NSF GRFP Fellow, a NASA Finest Fellow, a finalist for the Paul and Daisy Soros Fellowship for New Americans, and a Future Space Leader Fellow. So yeah, with that, thank you, Caroline, for coming here, and looking forward to your talk.
Thank you, Karen. Yeah, thank you so much, everyone, for coming to listen. This topic is definitely a little bit of an aside to all of the research that you all do, but hopefully will provide some context and maybe some new ideas to help you all shape all the work that you do, especially with like wildfires and aerosols in the NASA GISS model. So I would like to talk a little bit about my research that I've been doing here at Columbia University. My advisor is Park Williams. He's now based at UCLA. He was previously based at Lamont Doherty Earth Observatory. And I'm now in my 5th year, so this is the culmination of so far the first 2 projects that I've been working on. Next slide, please. Oh, perfect. So this scene probably feels very reminiscent of something you saw last summer, but funnily enough, this is not even a picture from last summer. This is a picture from July 21, 2021, when instead of Canadian wildfire smoke coming down to New York City, this is Western US wildfire smoke coming across. And I think it really just highlights the global impact of what the Western US wildfires are causing on New York City and on the entire US. And I think it highlights the important work that you all are doing on air quality and on aerosols. And I think advance slide one more time. And not only is it a an air quality problem for humans, but it's also an infrastructure problem where humans in the Western US are building outwards into the wildland-urban interface and therefore experiencing fires encroaching right directly onto their properties and endangering human lives directly and indirectly. And so this is from Jeff Frost during one of his art projects where he documented the 2020 California wildfires. Next slide. And so looking at the data, particularly, what's really cool to see is that in the news, we've been seeing highlights of fires getting bigger and bigger, and the data actually shows that fires have been growing larger. And in this case, this is just forest areas, so not including like savannas, grasslands. This is just the forests of the Western US. And we can see that since 1984 to 2022, fires have been increasing in area burned at this exponential rate. We put this trend line onto this figure. And it's really topped by those big fire years of 2020 and 2021. And then in this picture, just on the right here, I was in San Francisco for AGU last December, and I got to visit Big Basin State Park, which is like right near, maybe like an hour drive out from San Francisco. And I don't know if the contrast is good, but basically I'm down there with the big tree trunk down there. And what you can kind of see, but not really, is that in terms of the amount of area burns height-wise, is that the fire, the charcoal actually comes all the way up here from, in this case, the CTU lightning complex fire that happened in 2020 that burned like 60,000 acres of land, I think, in total, but only 1 person was killed in this event, which makes it actually quite a good event in that sense. But these areas are generally supposed to be fire, like they have frequent fire, and so they're pretty fire prone. But then I think what's happening, especially with these higher fire years, is landscapes that generally would be okay with fire and generally can recover and are very resilient to fire may be experiencing also more severe fire that could be taking out these kind of landscapes instead of helping with the natural growth of these forests. And so, next slide, please. And so another unique aspect of the Western United States is that in general, these landscapes, because they are used to frequent fire, what's supposed to happen is that we're supposed to see fires, forests have more like kind of cleared mountaintops, like in the image here from 1934. But there's been a history of a century of fire suppression across these landscapes where the US Forest Service, as they took in and like did their own forest management, they've actually suppressed fires, even natural fires that should be there to help clear the landscape. So we end up with more of an abundant amount of forests that could be fuel for fire on these mountainsides. And so in general, if we're thinking about the future of fire, like, and the types of the triangle of things, factors that drives fire, which is that you have to have ignition source, you have to have fuels available, and you have to have the right fire weather. So the climate has to be in accordance with starting a fire. Then what we have right here is we have abundant fuel, so therefore there's plenty of fuel to burn, and that might mean that we might have more fire in the future. And along that fire threshold, that fire exponential line that we saw in the previous slide. And in addition, Abatoglu in this paper from 2021 has shown that actually there is still plenty of fuel left to burn because not much of the Western US has burned in this past 40 years, and that there's much more room available to burn in the future. And this is where, like, the pink line is where maybe like one time there has been one burn, and then the red is where there's been multiple burns. But as you can see, that's maybe only like less than 20% of that forested area available. Next slide. And so if in this triangle of different types of factors that can result in area burns, if we have ignitions, which are usually lightning or human caused, and we have abundant fuel, then the last factor is climate. And so in the Western US, it's very interesting to study fire because then we can see that there is this very strong relationship of climate tied closely with area burn. So the figure on the left here is actually a figure that a lot of fire scientists study very closely, which is that as vapor pressure deficit as a proxy for aridity in the Western US increases, as this increases linearly, what we see on the y-axis, which is forest area burns, this increase is also exponential. So this relationship is really strong, where just an incremental increase of vapor pressure deficit results in that very strong exponential increase. And it's also very concerning that we can see that between the blue and the orange dots, which are before the year 2000 and after the year 2000, we see more blue dots towards these lower aridity values, and then more orange dots towards these higher aridity values, showing that in more recent years, the Western US has been warmer and it has been drier, and we're experiencing these larger and larger area burn. And 2020 is right here, and 2021 is right there, showing that actually this falls right in line with this exponential curve, and allows us to think, how can we then, or will we continue on this path because we have so much forest area left to burn? Next slide. And so just to summarize so far, what I've shown is that a lot of the current science around predicting burned area and studying burned area has been this close tie between climate and wildfire area burned. And therefore, we can then use this very strong climate area burned relationship to then study how future fire might happen, or how much future fire we might have because there's so much fuel. And also, this is actually a really great time that NASA GISS is creating models. We have all these CMIP 5, CMIP 6 models in order to study the climate side of things, and we can therefore forecast future fire. And if you go to the next slide, that's what my advisor has been currently working on, is understanding then what is the separation using CMIP 5, CMIP 6 model between the anthropogenic effects on aridity and the internal variability of aridity. And in this case, in this paper from Abatoglu and Williams 2016, he's found that if we look at area burns, which is the observed line here over time, and we we can then use CMIP5 and CMIP6 to take out the anthropogenic part, the anthropogenically forced part of aridity, to understand that maybe half of the total area burn that we've been experiencing between 1984 to present has been from the anthropogenic forcing. But there's also a huge component that also could be internal variability. And so I think for this research, I think it's really interesting because then we can then look into the future of like, will this trend continue? And if anthropogenic forcing has such a huge effect, can we then use our RCP 8.5 scenarios and all these other scenarios to understand better what might happen? But I think another huge thing for my research, if you go to the next slide, is that these models don't necessarily characterize the relationships, the teleconnections of the ocean, which is also anthropogenically forced and internal variability forced with the Western US climate. And so even though we have a strong connection of climate to fire, what we're still trying to figure out is what's happening with the ocean. And in this case, this particular relationship is showing within this is the tropical latitude band. So this is the tropical Pacific Ocean. And because of the Pacific Walker circulation in general, we have generally a cool east tongue, eastern cold tongue on the east side of the tropical Pacific Ocean, and a warmer western pool on the west side of the tropical Pacific Ocean. And I put this boxes here because if we subtract the west from the east, we have what we call sea surface temperature gradient between those two. And the colors here actually don't represent necessarily the cold and the warm sides. It actually represents a warming in the warm side and a cooling in the cool side of this tropical Pacific Ocean. However, in CMIP5 and CMIP6 models, the general overall ensemble mean of these models shows actually that because of anthropogenic warming, we maybe should be experiencing more of a scenario on the left here, which is actually the cold tongue is also warming and the warm tongue is also warming. So we're seeing this difference where this looks like a more of a La Nina-like pattern where we have a big sea surface temperature gradient between the east and the west. But on the west side, we have more of a El Nino-like situation. And so this really is this is actually like building up to what I want to know then is if we have this bias in the CMIP5, CMIP6 models, what does that mean for burned area? And so if you go down to the next slide here, I want to tie this all together in the last introduction slide, which is that sea surface temperature really does matter to Western US climate. And we can see this very well with this correlation map of vapor pressure deficit to the sea surface temperature gradient, where you can see the entire map is a positive correlation, meaning that that's a strengthening La Nina-like state between where we have a strong warming on one side and a strong cooling on the other side actually leads to higher vapor pressure deficit. So we're getting more aridity, which means that we could be getting more burned area. And if you go to the next slide, same thing with precipitation is we see that it's strongly negatively correlated. So a strong sea surface temperature gradient here actually leads to less precipitation, which still adds into the storyline of there's warming, there's drying, which means that we could be having more burned area. But there's a little uncertainty if we don't know if we can use our CMIP5, CMIP6 models to understand that. And so I want to then go back to our summary. If you go one more slide, I have two major questions that I wanted to cover with this research today. The first of which is that why does the climate-fire relationship work? And this is tied to the first graphs that you saw where as vapor pressure deficit increases, we get the exponential burned area. But I want to know, like, okay, that's an atmospheric condition tied to a condition on the ground. What is that mechanistic connection between them? Just so we can continue using this relationship in our model. And the second question is, how does the tropical Pacific Ocean affect Western US fire-related climate variability and burned area tied to that bias and that uncertainty that we're seeing with how sea surface temperature might affect climate, which may affect burned area in the future. And then I just wanted to speak quickly to the data used in this project, which is I created this Western US MTBS interagency wildfire dataset for WUMI 2, which combines a dataset that some of you may know, which is the monitoring trends in burn severity dataset. If you advance one more, it's a Landsat-based dataset, which is which covers satellite data from 1984 to 2020 of burned area greater than 4 kilometers squared. And because that only covers large fires are fires greater than 4 kilometers squared, I wanted to combine this data set with interagency data sets from US Forest Service, Fish and Wildlife Service, the Bureau of Land Management, and so on, in order to get a picture of smaller fires, in this case, greater than 1 kilometer squared. And that combined database actually then added this, effectively doubled the MTBS database, so it gave a better picture of fire frequency, which I talk more about in my paper. I won't talk so much about in this project. And then just to say that the climate data is from NOAA ClimGrid, and the sea surface temperature data is from NOAA's extended reconstructed sea surface temperature version 5. And then finally, fractional forest cover there is from the US Forest Service. So then why does the climate-fire relationship work? It's tied closely to this figure right here, and I want to investigate more of why this relationship holds. This paper is published in Geophysical Research Letters, and the title kind of gives it away, which is that it's the rapid growth of the large forest fires in this case that drives this exponential response. And so I have just a few slides on this. Next slide, which is that that large fires in general, this was kind of like the idea behind this project, is that large fires have more potential for growth than small fires. And if you start if you start with the elliptical fire model, generally if a fire is ignited from a single point in this raw thermal fire model, then it spreads in a forward fashion. What we expect to see is that as that flame front grows, which is that perimeter of the fire, that then the actual area of that fire grows quadratically in this case. And so this got us thinking like, okay, well, that maybe the exponential relationship has resulted from this idea that the radius and the area of the fire matters. And what we found is that if we go to the next slide, is that if we look at instead at individual fires, if we like go all the way down to the daily fire level, we look at individual fires and we look at how each fire grows on a daily scale, we find that this model that I've shown in the previous slide actually holds to be pretty true, where we have on the x-axis the total fire size before day end. So if you're just thinking about like a fire growing every single day, instead of mapping out like the days of fire, what I mapped out instead is what's that fire size? So we see the fire size progression over time. That's the x-axis. The y-axis is how much fire has burned on that new day of fire. So as a fire is growing, if hypothetically, if we had a line on this graph that just went straight, like it was a horizontal line like that, what it means is that as a fire is stepping through its growing, we expect to see the fire growing at a pretty linear rate of growth. So it's like, if it's growing 1 kilometer squared per day, these are log units, so 0 is like 10 to 1. So if it's going, so it's just 10 to 0, I'm sorry. So if it's going linearly, then we expect to see it like growing 1 kilometer per day, and then next day it grows another 1 kilometer. So it's stepping through this linear sequence. But you can notice actually that it's a positive line of growth. So it's actually not growing with a slope of 0, it's growing positively, meaning that with every single day, the fire is actually getting a larger amount of area in that day's growth of fire than the previous day. So a fire might start out growing 1 kilometer one day, but then as that fire is progressively getting bigger, then that means that actually the fire has more potential to grow even bigger. So it might gain like 2 kilometers the next day. It might gain 5 kilometers the day after. So it's like a compounding bank account where depending on what the fire's current size is, that means that the next size is going to be even larger. And so that, okay, actually you can go to the next slide. So this checks out really well when we then bring this all the way back, and it's explained more in the paper, but we bring this all the way back to the annual scale. because of this relationship where large fires have more potential for growth than smaller fires, this comes out very well when we look at the same plot that we had where every point is 1 year of fire, but instead I've broken it out by the bottom 25% by area of fires in each year versus the top 25% of fires in each year. And you can see that the line for the smallest fires in each year actually come out in an almost linear relationship with vapor pressure deficit. So as VPD increases, then most of these fires will increase in size, but increase in a more linear fashion. But if we look at the top 25% of fires each year, then those ones are the ones that have this potential to grow even bigger as vapor pressure deficit or any other measure of aridity increases. So I think next slide. So now that we've kind of established that fires in general have this very strong relationship between burned area and aridity, we can then use that relationship to understand better and use that relationship in models to predict what may happen to future area burns. However, the other problem that I've described in the beginning is that from our figure here from Richard Seeger in 2019 is that there's this observed relationship that is not seen in models. So in the second part of my research, what I really wanted to see is how is that tropical Pacific Ocean affecting Western US fire-related climate variability? Because it's not coming out in burned area, then I want to investigate what might be the impact of specifically the La Nina like strengthening.
It's unrelated to, it's just my computer.
Okay. Okay, no problem. So if you click forward one slide, I'm taking this trend and I'm now putting it into just the years of observed area burns that I have. So 1984, in this case, 1981 to 2022. And you can see that I've now defined the sea surface temperature gradient as A minus B in this case. So if you move one more slide. And so variables to also account for what if for an annual area burn, like what if that might be drying out fuel that leads to fire area burns. So we want to take into account all of those. And the stepwise linear regression model will find whichever variables are most highly correlated and then step through and keep adding variables until the Akaike information criterion, in this case, is no longer reduced by 2 points. And so one more slide. And so this is where I use my models in order to isolate that SSC gradient trend effect, because I only really want to understand what is this particular La Nina-like trend, what effect that has on burned area. So what I'm doing here is then the goal is to get that isolated influence. So I put in both the La Nina-like trend, but I also put in this hypothetical neutral trend where I simply take out the slope, and that way I can feed it into my model and then understand the seasonal climate effects, which in this case are the climate influenced by that sea surface temperature gradient trend, but also get this neutral climate, which is the climate that occurs without that trend. And the difference between those two climate effects becomes this isolated influence on each climate variable, which is 8 different climate variables across non-forest and forest regions across 18 Bailey-Ziegler provinces.
There are other trends in the system.
Totally, yes.
From women trends, trend. How do you know that taking out the trend, not actually just taking out a different trend, but it's actually influenced for this?
Yeah. So that's a great question, and in this case, like in order to try to only take out that particular trend, when I created this, or when we created this neutral sea surface temperature gradient trend, like we've tried to keep in a lot. We've only tried to take out that slope, the trend line here, and leave in the internal variable. I mean, not the internal, the interannual variability. Do not try to touch like seasonal trends of.
Oh no, I
Yeah.
realize.
Mhm.
Second, well, I'm gonna do a regression just on the internal variables,
Mhm.
and then do a regression on the whole thing.
Mhm.
But if there's a third factor that also has a trend,
Mhm.
that is actually influencing it, that isn't part of the model,
Mhm.
and like that's still there.
Okay.
And maybe this.
Yeah, I think what you're getting at is that yes, like this region, for example, like El Nino, La Nina, ENSO is affected by this particular region, but this is also connected with, say, like the Pacific decadal variability, connected with other kinds of sea surface temperature trends that affect.
Yes.
Yeah. Thank you for the question. And yeah, in this case, actually, the next step might be more in what might help with that, because if we go to the next trend after we've taken out this trend, we're putting this isolated influence, which is the difference between that climate driven by the observed trend and minus that climate driven by the neutral SSC gradient. We put it into model 2, and if we go forward one more slide, then we are comparing next we're comparing next the climate that we can then use to predict burn area. In this case, we're using climate influenced by the SSC gradient trend, which is actually, in this case, we want to make sure we keep in our relationship a lot of the observed factors, a lot of the observed variables, because we only really want to get that trend, but without like trying to say anything else about the climate system other than that trend. So we're using observed climate to be the situation where the SSC gradient trend is positively influencing burned area. Like we have the La Nina like trend already built into observed climate, and we're comparing that with this climate without the SSC gradient trend, which is observed climate minus that climate influence that we've gotten from model 1. So we're looking at these scenarios and putting that into model 2, where we can then predict annual area burned for each non-forest, forest region, and each Bailey-Ziegler provinces to get these two relationships of a burned area under the strengthening trend and burned area under this neutral trend. And that difference between the two burned area becomes this relationship of what is that La Nina like trend's influence on burned area specifically. If you go forward to this slide, This slide is really like the capstone of this research, which is showing that between the two models that I showed you, which is the red and the blue line, there actually is some kind of difference because those lines, if there was no influence from the La Nina-like trend through these statistical models, then we would see these lines overlap. However, instead, what we see is that the red line, which is our model situation with the La Nina-like trend, that red line is higher than the blue line, which is the situation if we took out the trend from when we took out the La Nina-like trend from our climate runs and then predicted burned area, that line is lower. So that difference becomes actually like that the possibility of maybe up to a quarter of the burned area that we've experienced in the past 40 years, that was influenced by the La Nina-like trend. And I want to break this down just a little bit further with my last few slides, which is that if we just look at, I first just want to point out from previous slides, we saw that really exponential increase in burned area. And if we break that into Bailey's eco-provinces, this has nothing to do with the models now. This is just the observed the observed trends in burned area across all these different regions. And we can see that a lot of that exponential growth actually comes from, first of all, it comes from forested regions. And a lot of it comes from this northern regions, which are areas of the Western US that actually generally experience fire with a frequency of more like 100 years. Fires, like rather than compared to the southwestern US, which experiences fires more of like fires every 5 years. But because those areas are increasing in fire even much more frequently than they've naturally had, we are seeing increases of 1,000% change in burned areas since 1984, and up to 4,000, 5,000% change in burned area compared to the year 1984. And meanwhile, in the southwestern U.S., I think in the more like grasslands, in the more desert regions, it's actually not so much saying that there hasn't been any fire, but it's rather saying that the trend in the fire has been pretty consistently flat, and we have high fire years and we have low fire years, which might be actually more of a product of that the fact that those landscapes are more fuel limited. So at some point, grasslands will burn out, there'll be no more fuel left, and the grasses will regrow, and then we'll have another fire year. So it cycles more so than these very fuel abundant landscapes that aren't fuel limited. But then I want to set this picture up because just to show you like where fire is happening. And then the next slide here is now this is taking out using our models and showing what is the effect of the La Nina-like trends on these particular fire regions. And in this case, every region is the percent area burned, which is from the numerator, which is the sum of the area burned from the La Nina-like trends over the overall total burned area, observed burned area trend. And we can see that actually it becomes kind of similar to the map that we saw previously of where fire is happening the most, but also I think it really highlights like these forest areas in like the Rocky Mountains specifically, where fire is actually very influenced by the La Nina-like trend. And I dug into just a slightly more of like why is it so high in these regions? And if you go to the next slide, if I break this down then by Bailey's eco-provinces a little bit, so I look at each individual landscapes of fire time series, what I can see is that you can see that in general, like yeah, these landscapes are very increasingly being affected by the La Nina-like trends. And then looking into like my models and looking into how that stepwise linear regression model captured different climate variables, what I found is that these forest regions tended to look for spring to summer vapor pressure deficit to most strongly explain burned area in these regions. So then it becomes, and then this spring to summer vapor pressure deficit is influenced by the La Nina-like trend and has increased vapor pressure deficit higher than it normally would under this neutral trend condition, which has resulted in this influence on burned area. So there is this very strong connection then that spring to summer vapor pressure deficit is being affected by what's happening in the tropical Pacific Ocean, which has this influence in overall on burned area. And then I also want to turn to look at, if you go to the next slide, in these like desert regions, what's interesting is that unlike the forest areas, all the forest areas generally see this increase in burned area because of the La Nina like trend. But in non-forest regions, actually, you can see that there's a little bit of a difference where in the south, what we see here is that actually the blue line, which is our model under the neutral trend, has more burned area than the red line, which is the model under the La Nina like trend. And this differs where from the north parts where actually the red line with the La Nina like trend is higher. So there's this like this north-south dipole pattern between what's happening from the La Nina like trend between these two areas that are mostly desert, like non-forest regions, mostly desert grasslands, savannas regions. And I think what I think has come out from that is by looking at the climate to burned area models and seeing what variables are selected for these areas, non-forest areas, winter to spring antecedent precipitation is generally selected, which holds up with a lot of the research that has been done before, because in these cases, that winter to spring antecedent precipitation is important for the growth of fuels in these regions. And what the La Nina like trend is doing to these regions is then, if you remember the correlation map where everything was blue, it's decreasing the precipitation in the south, which is important to area burn. So area burn decreases, but in the north, where there's actually a little bit more red correlation, where a little bit more positive correlation, where precipitation is increasing in those regions, leading to the growth of more fuel, which is leading to then more burned area in those regions as the sea surface temperature gradient is strengthening. And so my final figure slide is to sum up just those 2 points, which is that the strengthening SST gradient enhanced area burned across the Western US, but a lot of this influence comes from forest regions. And then this is seen very clearly with how forest area burned on the left here actually has this larger difference between our model with the La Nina like trend compared to our model removing that trend, versus non-forest area burned where we have this north-south dipole of forests either being enhanced or being suppressed by the La Nina like trend in terms of burned area, that adds up to seeing an almost like zero effect in a lot of the time series. And so last slide here, I just wanted to give a few key conclusions from all of this research that I've been doing, which is because of that compounding growth of individual fires, fire is responding exponentially to warming and drying across Western US forests, because we can see that larger fires are the ones that get larger on an individual scale, which then ties to overall all these larger fires getting extremely large when introduced to VPD and introduced to more warming and drying. Second point that I want to make then looking at the second paper is that an important contributor to aridity has been that La Nina like trend in the tropical Pacific Ocean with that tropical Pacific sea surface temperature. And that has added up to 1/4 of the observed area burns finally, if you go to one more point, then the tropical Pacific sea surface temperature gradient trend is not captured in models as we've seen with previous research. But the important part that this research highlights is that it has enhanced forest fires, especially because it's enhanced that aridity and the vapor pressure deficit during the summer months when fires are happening. But because this gradient trend is not captured in models, this adds this extra layer of uncertainty to already known model biases. And so when we're considering and forecasting future fires, we should definitely consider what is happening with our models with these connections between the Pacific Ocean and over the Western US. Thank you.
Thank you so much. We definitely have enough time for questions. Really interesting. So, I mean, I guess I'll just ask you to expand on the last point. And so I mean, I guess it was like the Seeger et al. 2019 paper was showing that I guess those six models weren't getting the gradient, but then they were also overestimating the change in SSTs for most of the region. And so what do you think, like if those models did have interactive fire relation in model B, would that lead to are destructive wildfires or just different variability? You know, what do you think about that?
Yeah, I think considering that the current La Nina-like trend resulted in more VPD over the landscape, and like the correlation in general showed that if there's less vapor, or sorry, if there's a weaker gradient between the east and the west in the Pacific Ocean, then that would mean that VPD would be lower. So I think yeah, adding that enhanced fire module would mean that if sea surface temperatures were correctly added to the Model E or to the NASA GISS model, and then you would see more fires maybe than our currently would be estimating.
But the converse, like, would be still bad.
Oh, what if
it's
still
in
bad?
terms of the,
Oh.
in terms of like the
Oh,
SSTs, would that lead to an overestimate of fires or just wrong annual variability or some underestimation?
yeah, it would be
It would
yeah,
be an
underestimation.
Okay.
Yeah. To what extent is
So,
still unknown, yeah.
I mean, is it an increase in like La Nina-like conditions, or is this kind of like the eastern subtropical Pacific global warming hold that's being upwelled somehow? So it's just the fact that part of the ocean is not really experiencing so much global warming as
Yeah.
the rest of the ocean basin. So I guess following on Gavin's question, is it really
Mhm.
like this La Nina-like thing, or is it like the
Mhm.
fact that you have like global warming that's happening, and so you could equally interpret your results not to be like increase in like La Nina-like trend, it could also be like this is the impact of like hot most of the Pacific Ocean.
Okay, I see what you mean. So like the rest of the ocean is warming at the same rate as the
So
model
that
estimate.
trend is
Uh-huh.
that trend an artifact of the fact that the eastern side is one of those places that's kind of funny places in the world that hasn't really had much warming.
Is it a product of I think it's to be determined, because I think what I'm not trying to show here is like the influence of anthropogenic warming versus internal variability so much. What I'm trying to show is that because in general that there is this strong teleconnection between this particular region and what's happening over the Western US, that is affecting fires. So I'm not trying to do an attribution of like, is this like overall a teleconnection of the entire Pacific Ocean and all the effects? But I see what you actually, I think I see what you mean. I think if we had more data, it would be easier to know whether this condition is just specifically like this 40 years, this particular tropical Pacific Ocean.
And you have Dorothy on here, and I'm sure you talked to the tree ring guys, like, and you can extend that
Mhm.
gradient back through time, certainly for another 100 years pretty easily. Coral records, and then you can
Mhm.
probably make similar kinds of nice reconstructions with the tree records or whatever historical archive. Have you tried that?
So I haven't tried that, but I have thought about that because even Park has worked with tree ring records of wildfires. I think for this particular study, I think with combining paleoclimate records with current modern records of satellite data, it's a little bit more challenging to actually relate these paleoclimate records, which are specific to like one basin, like one one basin or one region of trees with like the entire Western US. So I've kept this particular study more to just like this modern period of time. But I think it is very important to look back further in history because the teleconnection is not just this one particular part of the ocean. I think it is important to recognize that it is from all these different factors from different parts of the Pacific Ocean and the Atlantic Ocean, and that everything is not just a single system. It's all very connected. Thank you.
Sarah, but it seems like
Mhm.
though that your research is less focused on explaining why that trend and understanding why that trend is there, but the fact that that trend does exist, whether or not we call it global warming or La Nina, like what that trend then impacts the Western US. That's kind of, it seems like that side of it is more your focus.
Right. Thank you.
What is your model predicting for? I'm sorry.
So this model only has taken into account like the historic period. So I haven't taken into account the current climate for now, but that's something that I really do want to use the model for.
I mean, I feel like, I don't know if I missed it, but I have a couple of very questions about, like the, auto correlation of the temporal structure. Because, you know, are you taking that into account? Or are you just saying, VBD is, or relative humidity is correlated with things here? Burned area is anti-correlated, so it's a wash. Are you explicitly taking the temporal structure?
I think that's what. In this case, I might need to talk more with you afterwards because I think your statistics are probably extremely good and I could learn from them. In this case, if I can explain it, it's more like we are relating this sea surface temperature to this to just like climate over the Western US in either the current season or the prior season of sea surface temperature, if that makes sense. So that way we account for, like, because of the temporal effects, we want to make sure that we're only relating these two seasons that we know have this strong relationship and lead to what is happening with climate over the Western US. But in with climate itself, we're looking at the current year of with 4 different seasons that then affect burned area in that year, and then we're also looking at the prior year to say, oh, we're looking at what are the effects of this prior seasons of precipitation, temperature, and then how that might relate to the next year's burned area.
Are you doing a regression over like a bunch of different variables, right, which are all and correlated with each other?
So it's a regression, but it's a stepwise regression. So I'm looking for what variables are what single variable is the most related before I start considering other variables. So I'm not simply putting everything into a bucket because the effects of all these variables are very similar. Like precipitation is highly correlated to BPD, which is highly correlated to temperature, for example, and relative humidity. Instead, I'm looking at, okay, like what's first correlated? Maybe it's VPD in the summer season. And then I'll perform a regression again to look for VPD and what if I add another variable out of all of these lists of variables from current season, current year, and like prior year. And then if that reduces the FIP information criterion by 2 points, then I will consider now VPD and say the next variable, which could be temperature. And I'll keep doing that process to include more variables, but that way, by only considering one variable at a time, I'm not going to I'm trying not to run into the position of now I have all these variables that are extremely correlated with each other and don't really explain much more about burned area.
Just kind of going off the Maggie's question, less familiar with the questions, but can you more thoroughly explain the physical link between these learning and like conditions and the aridity it's the wildfire?
Yeah, I can explain it on more of like a surface level because climate dynamics is not really my field, but this is based off work where it's been shown that in general, for like ENSO, for example, like even though what I'm looking at is more of like what is the connection of this like decadal trend that's happening in the Western US, but this is based off of the fact that with just ENSO itself, which is, you know, every 2 to 7 years, in during because of the difference in the temperature between the colder eastern side and the warmer western side, that actually affects it affects both the Walker circulation, but also affects in general the propagation of waves over the upper atmosphere and shifts the jet stream. So that way, that actually changes what happened, or that actually affects, first of all, the high pressure region in the North Pacific, which changes the position of the jet stream to either shift rain and precipitation more to the southwestern U.S. during El Nino years, or shift rain more to the Pacific Northwest during La Nina years. And so that kind of dipole also comes out, I guess, with this more decadal trend where, especially in grasslands, what we saw is that there is this difference between precipitation in the north versus less precipitation in the south that then allowed fuel to grow in the north, but less fuel to grow in the south, which changed whether or not there was burned area in the north or south.
Statement allows there to be more fuel than we could potentially. That you could think that like less precipitation.
Yeah. It's very. I think it's unintuitive for regions that aren't very fuel abundant, because then it's more fuel. If it's more fuel limited, it results in these stronger links with precipitation in like this season that you don't really think would affect it as much. But in forests, for example, I think more importantly, it's actually more about BPD, which dries out the fuel that's already available in forests, but also could lead to grasslands fuel drying out too much that there's not even anything to burn. Yeah, that's why in this model, I wanted to make sure I separated forest and non-forest too, because those are just two completely different kinds of ecosystems that have fire.
Interesting. I have a question, and maybe you said you haven't missed it. So when you take out the SST gradient trend from the climate drivers, how do you take it out from the D and the percent and all the other?
Yeah, so I think if
You want to go back to
yeah, if you go back to slide, it should be around 21.
one more, or
I think, or what, one down. Yeah, so I take it out of the climate by using the first model, where I first take into account both like the positive La Nina-like trends, but I also take into account the sea surface temperature trends. And I can get a difference between both of these climate predictions that come out of this model to then go into the model 2, which is trained on the relationship of climate in general to observed climate to area. If you go down one more, then I'm comparing the observed climate then, which is I am assuming that I have the La Nina-like trend already built into that. So I'm comparing that to the observed climate minus that isolated climate that I got from the first model.
So it's the model when it's like a yeah.
So model 1 is also a stepwise linear regression model, but I get the climate for every single forest region, every single non-forest region, and for 8 different climate variables for 3-month climate seasons across 2 years. So it's like I'm running this whole statistical model training for like thousands of models that all predict climate and get the effect of the sea surface temperature gradients on climate in all these different regions in all these different seasons.
Great talk. Just out of curiosity, have you looked or considered looking at winds and surface winds? Because they also are important for a birder.
Yeah. So trends in surface winds are incredibly important for burned area, especially when thinking about like how each individual fire grows, especially because one wind has actually then like launched certain fire events like thousands of kilometers greater, and I think and it's something that I've actually put into the model. So I put in surface winds into the model, but it never really comes out as that important of a variable because on larger timescales of annual area burns, wind is just such a chaotic feature that it doesn't really lend itself to actually predicting whether or not a area burn will be bigger in general. I think because of just the sheer number of fires that happen and the the types of landscapes that fires happen over. And but I think for example, I think with like NASA's EIS, like the current fire modeling work that's being done, where it's like modeling how a fire is expanding right now, I think wind would be extremely important.
Thanks. I noticed that in lab model, even with the observed seasonal temperatures is unpredictable a bit compared to observations, particularly in the more recent decades. And I was wondering if you considered using something other than a linear regression model or model two, given that we saw an exponential relationship between.
So the question is like, because the relationship is nonlinear, that yeah, so I think that's a great point. And in these models, in order to capture that linearity is annual area burns for these models is predicted as a log of area burned, and that actually then allows the relationship to have more of a linear relationship in the statistical model, which results in when you unlog it, then it becomes exponential. But I think actually even with modeling, I'm sure that there are more statistical methods, and even I'm sure there's also machine learning methods to be able to model these relationships because they're so nonlinear and that they're so complex.
Okay, we're right about at 2 p.m. Yeah.
So the fire season. Okay, so my speculation, without being able to put it into my model yet, since I did not put in the climate, but because we had a really wet winter, and winters generally in the Western US is the period that determines most of the fire season. Uh, a very wet winter resulted in a lot of snowpack, so I think it could mean that this year would be a pretty small fire season. I don't think we should see a lot of area burns. But at the same time, what I've been seeing is that this summer is also predicted to be pretty high with vapor pressure deficits. So it's, I think it's still to be determined without having done any of the modeling, which I think if I put it in there, then we could see better.
Do we have any questions on that? Okay, maybe we can just wrap it up there and give another round of applause. Okay. And I think people know this, Caroline is here at Columbia for at least another few months. So she's around. Do you want to connect or anything? Gotta figure out how to get everything. Okay, and thank you to, well, there's no one else though. Okay. Thank you to everyone that came in person.